The time comes to introduce the concept of torque when we're ready to analyze the motion of a rigid body. So let's begin with a few words on this new way of modeling a moving system. We'll now have two options for modeling a moving system. The first one we have been using is the object model, in which we treat the system as just a point mass. So here by system, I could mean any macroscopic thing composed of zillions of independently moving atoms, like this chicken here. That could be our system. It's clearly complex, so we want to simplify things. We can do so by modeling the entire chicken as just a single point particle located at the center of mass of the chicken. And that's fine if all we care about is roughly where the chicken is, where the position of its center of mass is. And the physics we need is Newton's second law for a system. This tells us everything we would want to know about how the center of mass of the chicken is going to move. So that's perfectly good as long as we only care about where the center of mass is. But if we also care about, say, the orientation of the chicken, if we care about whether the chicken is right side up or upside down or spinning around in any way, if we care about orientation, then we need a more sophisticated model. So model number two is as a body. Model the system as a body, something that actually has volume and takes up space. We'll be specifically focusing on rigid bodies. Rigid here means something that is incompressible, can't be stretched or squeezed, and has no independently moving parts or joints. So our chicken doesn't really qualify. You can squeeze a chicken and it's got wings and legs that move independently, so it can't really be well represented as a rigid body. This wrench, on the other hand, there's our archetypal rigid body right there. You can apply forces to it and it doesn't seem to change its shape at all. It has no independently moving parts. It's just a chunk of stuff. That's a rigid body right there. Contrast that wrench with this wrench, which does have independently moving parts. So this is a compound machine that's more complex than a simple rigid body. So it's really this kind of wrench we're talking about, just a chunk of material. Okay, well, going forward, we'll be using this rigid body model to analyze how an object like this will move through space and also how it will rotate in space. But it's important to remember that nothing is truly perfectly rigid. No object made of atoms can be. So this wrench, when I apply forces to it, it does bend a little bit, even if it's hard to tell. And when I pull on it, it will stretch just a little bit. It's not perfectly rigid. Nothing is. But we're fine with that because we know that we're just making an approximation, a mathematical model for behavior. And a lot of objects can be well modeled as being nearly perfectly rigid, even though in reality they're not perfectly rigid. So this new model will be useful, in fact necessary, if we care about the orientation of the parts of the system. So if we care about whether the wrench is oriented like this, or indeed if we care whether the wrench is rotating in space, if that matters to us, then we'll need to use this rigid body model. We can still use Newton's second law. We can still use this to track changes in the location of the center of mass of the wrench, center of mass right about there, that imaginary point. We can still track that point using N2L, but if we want to track changes in the orientation, if we want to analyze the rotation of our rigid body, we're going to need some new equations. We'll need a rotational version of Newton's second law to track changes in orientation. So we'll be working towards developing this. The main idea we'll need is that of torque. Torque is this tendency of an interaction, meaning a force, tendency of a force to cause an accelerated change in the orientation of a system relative to some given point. Okay, so there's a bit to unpack there. We recall that in dynamics, forces being the interactions between objects, forces cause acceleration. Here, for rotational motion, torque plays the role that forces used to play. Torque will be the thing that causes accelerated changes in orientation. So torque doesn't just cause an object to rotate, it'll cause its rotation rate to increase or reverse direction. An accelerated change in orientation. More on that later. The symbol here for torque is the Greek letter tau. There's our tau, rhymes with cow. Here's how to draw it. It's actually kind of a short thing. It looks, to me, always like a one-legged pie. One-legged pie there, kind of a curly fancy top and a fancy leg, but just one leg instead of two. It's a lowercase Greek letter, lowercase t. So there's our tau for torque. And let's discuss what we mean by the magnitude of the torque exerted by some force about some point P. Note I said here that torque always has to be defined relative to some given point of rotation. P is our point of rotation. So by this symbol, we mean this expression. The magnitude of the torque exerted by some force about some point of rotation. You'll have noticed by this harpoon symbol that we're representing torque as a vector. More on its vector nature later. For the moment, let's just focus on what we mean and how to compute the magnitude of a torque. It depends on three factors. Factor one, the magnitude of the force that's causing the torque. So this one's obvious. The stronger the force, the greater the magnitude of the force, the more torque it will exert. So I've got three scenarios here, one in which zero torque is being exerted, then some torque, then more torque than before. In all cases, my object is this rigid body, this wrench here, the point of rotation, P, down here at this end. So we're imagining this wrench being able to rotate about point P. And if I apply no force, no torque. If I apply some force, like that, if I push it, I can change its orientation. If I apply more force, I'll change its orientation more dramatically. So that's the first factor. Stronger force, more torque. Next factor, the distance from the point of rotation. So if I apply a force right at the point of rotation, if I push the wrench right at point P, it's not going to rotate. If I push some distance away from point P, I will cause it to rotate. And the further away from point P I push, the greater the torque will be. Okay, so there's the distance being the second factor of three, and the third and final factor that influences how much torque is exerted is the angle of that force. Specifically, the direction of that force relative to the location of P, the rotation point. If I push directly at the point of rotation, if I push directly in, we know the wrench won't rotate. Likewise, if I pulled directly out, straight outwards, the wrench wouldn't rotate. But as here, if I push with a force at some other angle, we will get a rotation. And the way to maximize the torque we get is to push with a force making sort of, in this picture, a right angle to the wrench itself. That's our maximum torque. So we're going to put together these three factors into a mathematical model that will enable us to compute the magnitudes of torques.